In this video, I want to take a look at some of the applications of differential equations, and in specifics, I want to talk about how we model different physical phenomenon using differential equations, sort of generally speaking. So I want to look at three specific models. There are a bunch more in the book if you care to read it, but I want to start off with Newton's law of cooling, which actually isn't in the example section of the book, but there is a homework problem on it, so you'll see it there. So let me start with Newton's law of cooling, because I think it's a good intuitive place to start. Okay, so the idea when we're talking about Newton's law of cooling, which can be a misnomer. We aren't always going to be talking about something cooling off, but it could also be heating up. But the idea is that we introduce some object at some given temperature into some environment, and then that environment has a different temperature than the object, and we want to see what happens to the temperature of the object over time. So basically, we're just trying to see whether something cools off or heats up. So imagine taking a bag of peas, frozen peas, out of the freezer and setting them on your countertop, or a tray of cookies out of the oven and setting them on a cooling rack. What's going to happen to the temperature of those peas or the temperature of those cookies when you introduce them into a new environment that has a different temperature? So that is the point of Newton's law of cooling. So we're going to introduce some object, and that object can be the peas or the cookies or whatever, that is initially let me see if I can write correctly here, initially at some temperature T0 for the starting time into an environment that's at a different temperature. We'll call it T sub m. That's what the book uses. I don't know why they chose m, but T sub m. Let's think about what will happen in a few different cases to come up with a sense of what our model should look like. What is the behavior that we're wanting to capture with our model? So for example, what happens if our T0, our temperature of our object, happens to be exactly the same as the temperature of the environment? What should we expect the temperature of the object to do? Well, if you pull something that's room temperature out and put it in a room at that same room temperature, nothing should happen. The temperature should stay the same for all time. It should be a constant. In this case, the object's temperature, which is initially, we'll call it T by itself. So capital T is temperature. It's a function of lowercase t, time. So this is temperature. This is time. That object's temperature over time should be a constant. It won't change. Oops, won't change. And we should simply get that basically, so instead, T of t will just simply be equal to T0 for all time. So that's one thing that can happen. Alternatively, if we're talking about the case of the cookies, maybe T0, the temperature of our object, is greater than Tm, the temperature of the room that it's put into. And in this case, what we would expect to see is that the temperature should decrease. So in this case, then the object's temp should decrease, or T of t should decrease. over time. It should cool off. And alternatively, if we're talking about the peas coming out of the freezer, if our initial temperature is less than the room temperature, then the object's temp should increase. It should heat up to room temperature. So these are hopefully all fairly obvious ideas, but another question I want to ask is, what is going to happen to that temperature? So if we've decided that the temperature is cooling off, in this case, our middle bullet point here, the object's temperature is decreasing over time, what does that tell me about the rate of change of the temperature as a function of time? So here I've got t as a function of t. What happens when I take the derivative, d capital T, d little t? So the rate of change will be the derivative t prime, essentially, if you want to think about it that way, or d capital T over d lowercase t. We'll write that out in just a minute. But needless to say, what should happen to the temperature, the rate of change of the temperature over time? Well, in this case, we know because the temperature is decreasing, the rate of change must be negative. That would be what would be required for the temperature to go down. In this other case, the rate of change must be positive because the temperature is increasing over time. But is the rate of change going to be constant? So let's come back to this second bullet point. We brought out the cookies. We set them on a cooling rack. We know the rate of change of the temperature is negative, meaning it's cooling off over time. Is that rate of change going to stay constant? So maybe it cools off 50 degrees Fahrenheit per minute, right? So after 1 minute, we bring the cookies out, they're 350 degrees. After 1 minute, they're down to 300. After another minute, they're down to 250. After another minute, they're down to 200. After another minute, they're down to 150. After another minute, they're down to 100. After another minute, they're down to 50. After another minute, they're down to 0. After another minute, they're down to negative 50. Does that make sense? Should the temperature just keep decreasing forever? And the answer to that is hopefully obvious to everybody. The answer is no. This shouldn't just decrease at a constant rate. The rate of change is not going to be constant. Eventually, you would expect that the temperature of the cookies should approach the temperature of the room. If the room's 70 degrees, the cookies are only going to cool off down to 70 degrees. So this tells us something about what type of behavior we're looking for our model to produce. When it's all said and done and we've come up with our model and we solve it, we want the long-term behavior of our model to be that the temperature T of t decreases down to whatever the value of Tm is, whatever the room temperature is for large values of time. An hour, 2 hours later, the cookie should be down to room temperature. That's what we're talking about. So what that tells me is that definitely our rate of change of temperature is not going to be constant. And in fact, what makes sense is that the bigger the difference between the temperatures, the faster that it's going to cool off or heat up. So, for example, if the cookies come out of the oven at 500 degrees and we take them outside in the middle of winter where it's 0 degrees, I would expect to see quicker cooling off in terms of the rate of change than if I brought out cookies that were 150 degrees into a hot summer outdoors where it's already 100 degrees. Those should be cooling off less quickly. So basically what I'm suggesting is I think that the bigger the difference between the temperatures, it makes sense that the bigger the difference between the temperatures, so the larger the temperature difference between the object and the environment, the faster the rate of change. And whether that rate of change is positive or negative obviously depends on in the case, but I would expect a larger temperature difference to yield a faster rate of change, faster cooling or faster heating. So basically what I'm suggesting is that the rate of change, d capital dt, so dt dt, but d capital T d lowercase t, which is equal to our rate of change of temperature, should be proportional to whatever the temperature difference is. And the symbol we use for proportionality looks like this, kind of. That was a poorly drawn one. It's kind of like the little Jesus fish type shape, kind of, I don't know, is proportional. So I'll just put that in words here. Is proportional. That's what that symbol means, to the temperature difference. So what I'm suggesting is that dt will be equal to some constant, I'm going to call it k, times the temperature difference. And this constant is the constant of proportionality. So it's going to be the temperature difference, the current temperature T minus the room temperature Tm. So this is basically what our equation is going to wind up looking like in this case. So let's just think about this for just a minute. We know that initially, at the initial point in time, the temperature is going to be T0. That's our starting temperature. So at time 0, the initial temperature is T0. Over time, the temperature is going to change, and this is the variable capital T that we're trying to keep track of. I want to solve for this capital T. This is the dependent variable that we want to ultimately solve for. It is a function of time. It is going to change over time. And our suggestion is that we think that the rate of change is proportional via this constant of proportionality to the difference between the current temperature of the object and the temperature of the room. So this is basically now a differential equation. We need to make sure that it follows all of these bullet points that we had up here. So the first thing we can do is check this first bullet point. What if T sub 0 and Tm are the same thing? So what if the object is the same temperature as the temperature of the room? So what happens if I plug in T0, but I know that T0 is equal to Tm? So if T0 is equal to Tm, and I plug that in right here, these two things are the same. Their difference is 0. And no matter what this constant is here, I'm going to have the whole right-hand side be 0. If T0 and Tm are the same, if the temperatures are the same, this will be 0, and our rate of change will be 0. What does it mean for the rate of change to be 0? It means it's not changing its temperature, which is exactly what we expected to see up here. If the initial temperature matches the room temperature, the object's temperature shouldn't change. It should just be a constant. It should just stay at T0, which is the same as Tm, for all time. What else do we know? Well, if we look at these two bullet points here, these have to do with, we want hot objects to cool off to room temperature, and we want cold objects to heat up to room temperature. So we need that to be reflected by our model as well. So I want to think about what are the properties of this value k. So what do we know about k? So let's go back to these. If the temperature that we're using, so at a given, whatever given point in time we're at, if the temperature T of the object is greater than the room temperature, it should be cooling off. And if it's cooling off, that tells me that dt should be less than 0. It should be negative. It should have a negative rate of change. It should be cooling off, right? This means cooling off. So let's see how that would play out. If, as I'm claiming, this value of T is bigger than Tm, so T is bigger than Tm in our model up here, this quantity would be positive. This number is larger, and we're subtracting off a smaller number. So 150 minus 70. That's going to leave us with a positive number, in that case, positive 80. So we get a positive result out of this. This is the rate of change. What has to be true of k in order for the rate of change to be negative, less than 0, so that this object is cooling off? Well, that tells me that k has to be negative, because I want this to be negative. This piece is positive. How do I make the whole right-hand side negative? The only thing I have left to do is change k to be a negative number. Similarly, if the temperature is less than the room temperature, then we want our rate of change, dt dt, to be greater than 0. We want it to be heating up. And same thing goes over here. If this number is smaller than this number, so if t is less than tm, then this difference would wind up being negative. But to make the overall rate of change positive, again, k would have to be negative to undo this negative and make the whole result on the right-hand side positive. So between either of those two bullet points, these both indicate that k must be negative. Otherwise, hot objects will continue to heat up, cold objects will continue to get colder. They will move away from room temperature instead of toward room temperature, which is not what we want. Okay, the last thing I want to mention, so we know that k is negative, but now I want to think about not a few other things. One last thing. Imagine I take a cookie out of the oven, and maybe that cookie is sitting on some parchment paper. Maybe we cooked it on parchment paper on top of a baking sheet. If I take all of those things out of the oven at once, what's going to happen to the temperature of the cookies relative to the temperature of the parchment paper relative to the temperature of the baking sheet? Well, they're all going to cool off at different rates because they're all made of different materials, right? That piece of parchment paper, if I bring a piece of parchment paper out of the oven, I can touch that with my hands, even if I just brought it out of a 350-degree oven. Paper cools off very, very quickly because it has a very, very high thermal conductivity, meaning basically the room temperature is almost immediately translated into the paper once we pull it out. Whereas certain objects are going to radiate their heat much, much more slowly. So things like the cookies, they're going to cool off a lot more slowly. The cooking tray, probably similar to the cookies. Right? If I take a ball of lead or something and put that in the oven and heat it up and take it out, it's going to take a long time to cool off. It's why, for example, if you cook with cast iron skillets, they take a long time to heat up, but they also take a long time to cool off because they have so much sort of thermal inertia, if you will. They retain heat really well. They don't change their temperatures very quickly. So this is going to be another property that K is going to take care of. K is a constant. So note that K is a constant that's related to the thermal conductivity of the object. So hopefully that will make some sense as well. So for now, I'm not going to bother solving this differential equation. We've got it right here. So this is our differential equation. This is the important piece. We're not going to solve it yet That's going to come up in chapter 2. We'll start learning about different techniques to actually solve differential equations. For now, I just want to understand where those differential equations come from. And then down the line, when we solve it, what we'll do is we'll come back to this model and try to recognize whether it does indeed meet all of these bullet points that we talked about, and that the behavior matches our intuition that we had when we set up the problem to begin with. So this is one model. And this is the stuff that goes into it. We're trying to condense, in many ways, complicated mathematical ideas into some common sense physical phenomena that we have some intuition for just based on our observations of the world around us. And this is how a lot of these came to be to begin with. So the next one I want to talk about, the next model that I want to look at, is a model for population growth. So let's look at population growth. So again, we could be talking about trees in a forest, bacteria in a petri dish, people in a city or state or country. These models can apply pretty generally. So we want to model the growth of a population. Presuming it's growing, it may be decaying. Maybe the population is going to be decreasing. We'll see. But we want to model the growth of a population of things like, like I said, trees, people, bacteria, rabbits, whatever, over time. And this model actually goes back a long way to the late 1700s. A guy named Thomas Malthus proposed this model way back in 1798. It's a simple model. It turns out when you actually solve it, which we will do eventually, it has pretty good predictive power under certain conditions. And that's something I'll come back and talk about. These are models. We're trying to predict some behavior, but the models themselves aren't necessarily going to be perfect. So when we finish wrapping up talking about these models, I want to come back to them all and just see if we can point out some flaws. Are there any things or assumptions that we're making about these models? So let's just talk about this one, though. So this is sometimes referred to as the Malthusian model of population growth, named after Thomas Malthus, the person who first proposed this. Essentially, what his big idea is that the larger that the current population is, the more mating pairs there are. In the case of bacteria, the more reproducing pairs there are, or reproducing individual cells there are. And so therefore, the faster the rate of growth. So this comes from Thomas Malthus and is based on the idea that the larger the population, larger the current population, the more reproducing pairs, or whatever, maybe individual cells, doesn't have to be pairs. And hence, the faster the growth. So, essentially what we're making is a statement about dp dt. So this is the rate of change of our population P with respect to So WRT there just stands for with respect to time, T. And what we're suggesting is that the larger the current population, the larger the rate of change. The smaller the population, the smaller the rate of change. Essentially, we're making an argument about proportionality again. So essentially, the rate of change is proportional to the current population. So again, writing that out mathematically, we have dp dt is proportional to the current value of p. If we write that using a constant of proportionality instead, so that we can get rid of the weird proportion symbol and instead use an equal symbol, it's equal to some constant times p. That's all that it means. In this case, instead of using capital K for our constant, I'm going to change the letter to r, lowercase r. This is the letter that's typically assigned to this variable, and you can think of it as basically the kind of growth rate. Some species produce very quickly, some produce more slowly. So, the rate of change of a town of 100 people that are, imagine them, some closed environment, 100 people reproducing is going to grow that population much more slowly than 100 bacteria reproducing, which will grow the population very, very quickly. So this R has to do with the reproduction rate. And so in this case, we'll see what's going to happen, but we just said that we want the rate of change to be basically positive. So we want the population growth to be positive because we're assuming that the population is going to continue to grow as these pairs mate. So the assumption here is that it's positive. Down the line, we'll again talk about some cases where what happens if the population, the rate of change of the population is negative? What happens if we have, instead of a growing population, a decreasing population? What are some circumstances where that could happen, and how can we model that? So we'll talk about that in just a minute. But for now, we're assuming that this population can only do one thing. It can grow. And what that tells me is that I want this quantity to be positive so that our rate of change is positive. The population itself has to be positive. It doesn't make sense to even talk about a negative population. What does that even mean? And so if I want this to be positive and it's equal to this over here, I know P itself has to be positive to keep the whole right-hand side positive. The assumption is that R itself, R, which is our some sort of combined growth rate here, is positive. So R has to be greater than 0. Okay, so again, we'll talk about what happens. This is actually a problem that we may have solved depending on who you took for calculus and calculus 2. You may have already solved problems similar to this. But it turns out there are some weird things that can happen because this, again, assumes the population can only go up. And it's going to ultimately lead to exponential growth is what we will see. So we'll eventually come back and solve this, but that's for another day. For now, we're just going to stop with this model, but I want to think about those restrictions. It's assuming that the growth rate stays positive, that P is always positive. This population can only grow. It can never decrease. So this is fairly unrealistic. It tends to be a pretty good predictor of populations early on, but no environment can sustain indefinite growth. So this is accurate for typically small values of t, whatever that means. Small values, depending on the value of r, small values of t could be, minutes, hours, days, years, decades, depending on whether you're talking about bacteria or humans or something in between, right? So this is accurate for small values of t, but no environment can sustain indefinite growth. So, what's a more plausible model that works around this? It turns out that if we start to think about the environment and taking the features of the environment into account, we can come up with another model that's going to basically take the limitations of the environment into account. So, can we take the limitations of the environment into account? And the answer is yes. So, a more plausible model might assume that there is some maximum population that the environment can sustain, right? Based on the amount of consumption, the amount of resources that the population uses, there's going to be some maximum size of a population that that environment can sustain. So it makes sense that there might be some maximum population that the environment can sustain. And I'm going to call this population capital K. We're going to refer to it as a carrying capacity. So we'll call this maximum population the carrying capacity. And refer to it with the capital letter K. So let's start off with the same model that we had before. dP dt is equal to R times P. So this was our infinite growth model. It just keeps growing on forever and ever and ever. How can we modify this with this additional notion that the environment can't sustain indefinite growth? Well, what we would expect to see is that over time, as this population grows and gets larger and larger and larger, we should eventually expect the population growth rate, this dP/dt, the rate of change of the population, should start decreasing, meaning the population might still be increasing overall, right? The population could still be growing, but it would be growing less quickly. Essentially, what you would see is maybe the curve is going up, but eventually while it's still going up, it's not going up as quickly. It's starting to level off. And we would expect it to level off to this maximum value. I can write this maximum value K. That should be the maximum height that it eventually gets to. So this is kind of the idea. Incidentally, what happens if you start the population above the carrying capacity? What if you introduce more people or more bacteria, trees, whatever, into the environment than that environment can sustain? Well, in that case, you expect to see a mass die-off. If there's not enough resources, not enough food, whatever the resources is we're talking about in the environment to sustain that population, you would expect to see the population eventually go down. So if you think about it like this, and eventually, when we start solving the differential equation we'll eventually come up with, this is what we wind up wanting to see. There's going to be some level here. So you can think of this as being time, this as being the population, and this is our carrying capacity K. If you start your population somewhere down here below it at time 0, right? Time 0 is right here on the t-axis. Here's 0, so here's time 0. If the population is down here, we would expect to see it grow, but eventually level off. And if we start the population very, very small, maybe it even grows quickly and then eventually levels off. But if we start the population up here at a higher level than the environment can actually sustain, higher than the carrying capacity, we should expect to see a die-off that should eventually go down to the carrying capacity, to something that it can sustain. So these are the types of solutions I would expect ultimately out of this model. How are we going to capture this behavior? And again, we'll eventually see graphs like this once we solve everything, but intuitively, that's kind of the behavior that I'm expecting to see. Well, the idea is I want to adjust this so it doesn't grow in proportion to the current population, because we saw that eventually that would lead to indefinite growth, and it wouldn't meet this criteria that we're looking for. However, if I put in this factor here, if I do 1 minus P over K, let's talk about why I put this in there. This could still work. So again, this is still our growth rate. We still have time. We still have our population P. And this is our carrying capacity of the environment. What does adding in this term do? Well, when P itself is tiny, so when P is small, this whole term essentially will also be small. We're dividing by some large value K anyways, so this number is going to be small. This whole thing would be close to 1. So when P is tiny, essentially what we have here in parentheses is just going to be the number 1, and we'll get the same growth that we expected to get before. So for small populations, when we're not near the limitations of the environment, we expect to have this exponential growth. We expect the model that we had before to make sense. And it does. Whenever this whole thing in parentheses is essentially 1, this whole thing in parentheses is essentially 1 whenever P is tiny, whenever P is relatively close to 0. But what happens as P increases? So as P increases, this term over here wants to make our population growth rate also increase. So the population is growing, and in fact, it's growing at an increasing rate as the population grows. That's what this term does. But over here, as P gets larger and larger, this term is going to become more significant, and this number is going to climb or decrease from a value of close to 1 when P is 0, down to a value eventually that should get close to 0 when P gets to be the same thing as K. When P and K are the same value, so if our population eventually gets to the carrying capacity, this ratio should be 1. We'd have 1 minus 1 would give us a 0 in here, and the overall growth rate should go to 0. So this is one of the things that we wanted. We want dp dt to be greater than 0 whenever P is less than the carrying capacity K. So we want growth whenever the population is below the threshold of the environment. Let's see if I can write that as it looks more like a capital P and a capital K. We want dp dt to be equal to 0. We don't want anything to change. When we're at the carrying capacity, the population shouldn't be growing anymore. We've reached our maximum whenever P is equal to K. And indeed, that's what this does. When P is equal to K, again, when P is equal to K, this ratio becomes 1, and everything in parentheses becomes 0, and therefore the rate of change, dp dt, is equal to 0. And lastly, if we start off with a population that is above the carrying capacity, so if P is greater than K, if our population is larger than the environment can sustain, I should expect to see a die-off. I should expect the growth rate, the rate of change, to be negative. It should be less than 0. And again, this captures all of those behaviors. If P is a value larger than K, then this ratio will be larger than 1. I'll have 1 minus something bigger than 1, and this result will be negative, which will make the whole right-hand side be negative. So this model satisfies all three of these criteria that make some sense. This is called the logistic growth model. So logistic growth model. And it's a more accurate model of how things actually work. So logistic growth model. And did I name this one up here? Maybe I never actually called it. Right here, this one is. This one here is the Malthusian model. So here's our Malthusian model, and down here, this one right here is our same assumptions about R. R is still positive, but this is our logistic growth model. There we go. So it's more realistic. So we're going to look at one more model, but before we do, I just want to talk about some of the limitations of the two that we've already looked at. While we're at it, while this one's fresh in our mind, let's talk about this one. We already saw that we can create a model, and then when we think about the behavior of that model, it may not always work, right? We said this is accurate when the values of t are small, and essentially when the values of p are small, the small population early on. But eventually, this is just going to cause indefinite growth, and environments can't sustain that. So how can we modify our model to take that into account? Well, here's an improved model. So the idea is we're trying to model some phenomena. We're trying to predict something that exists that we can observe in real life, and we're trying to use math to make predictions about it. That's the point of a model. But the point I'm getting at is models are just models. They're just predictions. They don't tell us how the world works. They simply are meant to try to describe how the world works. And this is actually a philosophical point that people can get bogged down in. When you start to getting into complicated mathematical models of the universe and stuff related to, Einstein's theories of general relativity, all of these various things, the question becomes, for a lot of people, is this model the rule of how things work, or is it simply a description of how things work? So essentially, is there a rule and the universe follows this rule and we've discovered the rule? Or do things happen according to some rule or maybe not according to some rule out there in the universe? And this is just humans' best attempt to describe what we observe. And again, that's a philosophical debate that I don't want to get into. Basically the question is math discovered or is it invented? Do humans create these models or do we discover these models? If we create them, then they're just descriptions of the world. If we are discovering these models, the implication is that they existed out there before humans, and we're sitting around waiting to be discovered, and they are truly how the world works. When it comes to models like these, clearly these ones are invented. They're just going to be descriptions of how things work, but there's limitations. So for example, this one doesn't take into account really more than one species, right? We're only talking about one species in this model. It jams everything having to do with carrying capacity, be that limitations on the amount of land or limitations on the amount of resources or air or whatever, all into this one variable k. There's limitations to this. Tiny things. For example, if you think about mating pairs, if we're talking about people, what would happen if I plug in a population of 1? Well, according to this model, if I start off with my population at 1, in both cases, it'll eventually still grow up to the carrying capacity, or in this case, grow indefinitely. But in real life, if I start with a population of one human being and they don't have a partner to reproduce with, eventually they're just going to die out. There is no possible growth rate. So even in that case, these are approximations. In this case, they're continuous approximations of what in reality we normally think of as a discrete process, right? We don't typically say, oh yeah, this environment has, this city has 3,492.67543 people, right? It has to have whole numbers. We refer to people as whole people, not fractions of people. And so in reality, the way we talk about population growth is discretely, but our model is continuous. So there's discrepancies there that we need to be aware of. Up here with Newton's law of cooling, we assume that when we take the cookies out of the oven, they're going to cool down to the room temperature. But the reality is the room itself isn't necessarily going to stay at a constant temperature, right? When you bring the cookies out, the air in the room is going to cool the cookies off, but simultaneously the cookies are going to heat up the air in the room. And so we assume that this Tm was a constant, that it was fixed. The temperature of the environment was fixed. But the reality is this is going to be something that changes as well. So this is an assumption we made, or another limitation of our model. A limitation of this model is that we assumed the room temperature is fixed, that there's some infinite reservoir of, whatever the heat of the cookies is going, it's going off to infinity and kind of disappearing in some infinite black hole away from us that's not affecting the temperature of the room. And again, it works because most of the time we're dealing with fairly large room and a fairly small tray of cookies, so the temperature of the room isn't changing all that much. But the reality is it does change. We're also not taking into account any spatial things, right? The temperature at the ceiling of the kitchen is going to be warmer than the temperature at the floor of the kitchen because heat rises. Right? That's not taken into account at all. We're just assuming one constant temperature for both the room and the cookies, right? The surface of the cookies should be colder than the center of the cookies. So all of these things are assumptions or approximations, and this is the important point I want to get at when we talk about models. Models are wrong. Every mathematical model that we use to try to describe some physical process like this is going to be wrong. But it doesn't mean that it's not useful, right? We are assuming that we're aware of the limitations of our model, of the assumptions that we're making, of the constraints on the model, of the shortcomings of the model. And I want you to be aware of those when you start thinking about these things. All we're trying to do is come up with a model that gives us some insight to a problem. It isn't always going to be perfect. So that's something I want you to keep in mind. The last model that I want to look at is something we refer to as mixing problems. So you can think of this as a chemical process, if you want, or mixing solutions in some vat. So these are mixing problems. Well, I'll just call it mixing. So imagine that we have some fluid with salt in it or sugar in it or something, and we're keeping track of the concentration of that solution. So essentially that's the idea. We've got a solution. Imagine a solution, be it a salt solution or a sugar solution or a solution of some other thing. I don't do chemistry, I only cook occasionally, so salt and sugar are all I'm going to be mixing. But if you're doing chemistry, some reactant or something like that, some catalyst, imagine a solution of concentration capital C. So C is the concentration. And imagine that we're taking the solution and we're pouring it and mixing it into a big container with a volume of V. And that container contains some other solution, or maybe the same solution, but just at a different concentration. So imagine a solution of concentration C being poured and mixed into a container of volume V, capital V, that contains a different concentration. So maybe it contains pure water. Maybe the concentration in that is nothing. So different concentration. At this point, the mixed fluid is then siphoned out of the container, or poured out of the bottom, or drained from the bottom. So then the well-mixed, and we're going to assume perfectly mixed, that's again going to be another assumption, the well-mixed combined solution of what was being poured in and what was already in is drained from the container, or siphoned from the container, some way removed from the container. And in this case, let's assume that the rate that the original solution that's being poured in is equal to the rate that the overall mixed solution is being drained. So let's assume in this case, and we'll talk about what happens if we relax this assumption later. Let's assume the rate that fluid or that the solution is poured in that matches the rate that it's drained. All we're doing by matching these two rates and making them the same is ensuring that basically the volume of fluid in the container isn't going to change. If we're pouring it in at a gallon a minute and we're draining it at a gallon a minute, the volume of fluid in the container is going to be unchanging. So let's draw a little picture just to maybe make this a little bit more clear. So we've got some sort of spigot that is spraying in fluid into a big container. Here's our large container. It contains some fluid. And then we're draining fluid from the bottom of this container, shooting out of the bottom. And what we're saying is that the rate that it's coming in, is going to be equal to the rate that it's going out. So I'm going to use R for our rate. So R in is the rate in, so let's do it this way. This will be a better way to do this. Okay, let's call it, here's the rate, and here's the concentration. That it's coming in. Here's the rate that it's leaving, and the concentration is unknown because it's well mixed. So we don't know the concentration that it is leaving. And inside, our volume is V. Okay, so here's kind of the picture. We're pouring stuff in, it's getting all mixed up, and then it's being drained out. This volume V should be fixed because the rate in is equal to the rate out. So this is fixed because the rate in is equal to the rate out. So let's define a few things. I'm going to let Q be the quantity of whatever this is that we're mixing in. So we talk about a concentration. I mentioned a minute ago the concentration of maybe it's sugar water or salt water or something like that. Q is going to be the actual amount of sugar or salt or whatever. So Q is going to be the quantity of our solvent, whatever we're plugging in. So I'll just call it whatever chemical that we're adding. Maybe it's salt or sugar. And let's keep track of it in pounds. So it's a quantity in pounds in terms of weight. R, again, is our rate of input or output. They're both going to be the same. Our R in and R out are both going to be equal to R. They're the same. And let's keep track of it in gallons per minute. That would be a rate, right? How many gallons of fluid are being poured in every minute? How many gallons of fluid are being drained every minute? So it has units of gallons per minute. Hence, it is a rate. C, we already mentioned, is our concentration that's being poured in. And it's, so concentration of input, let's say. And it's going to be in pounds per gallon. That's how we would measure a concentration, right? The quantity of the salt or sugar per gallon of fluid. So the concentration should be pounds per gallon. V is our volume of our tank, or essentially the volume of the fluid in the tank. And it's going to be in gallons. And lastly, we have T, which is going to be time. And the unit of time that it looks like we chose to use up here, based on the way we decided to pick our rates, was minutes. So here are a bunch of different quantities that all make sense that they might relate to this problem with the appropriate units ascribed to each one. The question is, we want to know how much salt or other chemical, whatever the chemical is, how much salt or other chemical is in the tank at any given point in time. And ultimately, how quickly is that amount changing? How much salt or other chemical, whatever it is in the tank at time t. And how quickly is that amount changing? So, a couple of things to think about here. So let's take a step back from the math and just think big picture. If we're pouring in a fluid and that fluid is coming in at a concentration of maybe, let's just say 1 pound of salt per gallon. So concentration C of our input is 1 pound per 1 gallon. If the tank here is initially pure water, what's going to be happening to the amount of salt in the container? Well, as this fluid comes in, it's introducing salt, and we would expect at time 0, the amount of salt in the tank is 0. And over time, it would start to increase. And it would continue to increase over time, eventually reaching the point that the concentration in the tank matches the concentration of what's being poured in. Basically, over a long period of time, we're going to approach almost all the fluid in the tank having come from the input spigot, and all the water that was originally in the tank will have been, again, well mixed, but it will have been drained out of the tank. And so we'll eventually approach a quantity of salt in the tank that matches the input concentration. So basically, the concentration would be going up over time, and the quantity Q of salt in the tank, therefore, would be going up over time. Alternatively, maybe we have a really high concentration to begin with. Maybe initially it's something where it's like 5 pounds of salt per gallon early on, and we're pouring in something that only has 1 pound of salt per gallon. Well, in that case, as this mixes, we would expect the quantity of salt in the tank to eventually lower to the point that the concentration within the tank matches the input concentration of 1 pound per gallon. What I'm suggesting is it all is going to depend on the initial behavior. And we saw that before in these other problems, right? Depending if the population is initially above the carrying capacity, we'll see a decrease in the population. If it's below the carrying capacity, we'll see it increase up to the carrying capacity. If it's right at the carrying capacity, we'll see no change. The behavior that we see depends on the initial state of our system. And that's same thing is true up here in the temperature one, right? The peas heated up, the cookies cooled off, and something that's already at room temperature will stay at room temperature. All of these cases here, it's important to know what is the initial state of our system. And this is something called an initial value problem. We skipped over this section. It's section 1.2 of the book, if you want to kind of glance through it and read through it a little bit. But we're going to be coming back to this concept in the future. I don't think it was important to go through it this early. So we're going to kind of come back to the idea of an initial value problem later on. But I do want to point out the initial state of our system, of whatever we're modeling, is going to affect the ultimate behavior. The initial value, the initial temperature, the initial population, in this case, the initial amount of salt in the tank, will affect what type of behavior we see over time. So just keep that in mind. The initial value is going to play an important role, and we'll talk about that later on. It will become more meaningful once we actually start solving these types of equations. So we'll talk about it more in chapter 2. But for now, I just want to mention we skipped section 1.2. It all talked about this initial value idea. You're welcome to read it, but it really boils down to that one idea. The initial state of the system will affect the behavior of the system over time. Okay. So ultimately, we want to answer the question of how much salt, in this case, is in the tank at a given time t. But to do that, we are going to actually answer the second question first. How quickly is the amount of salt changing? So we're going to talk about the rate of change, same as we did with the other ones. Let's start with the derivative. Start with dq dt. So this is the rate of change of salt in the container over time. It's going to be equal to the rate of Q that's coming into the tank minus the rate of Q leaving the tank. So it's the input rate minus the output rate. That's going to be our rate of change. The overall rate, we have some salt coming in, we have some salt coming out. The overall rate of change will be the difference between those two rates. Hopefully that makes some sense. But I want to think about the units. The units will help. What are the units of dq dt? So let's come back up to here. Q was the quantity of salt in this case in pounds. T is time in minutes. So dq dt is pounds per minute. The units of dq dt are pounds per minute. And that means that over here, these need to have units of pounds per minute. Right? The reason that they have to be the same is we have an equal sign here. We're claiming equality between, they both need to represent the same thing. They need to represent the rate of change of pounds of salt over time, in this case, per minute. So I need to figure out how quickly is salt coming into the tank, how many pounds per minute of salt are coming in, minus how many pounds per minute of salt are leaving the tank. That is our goal. So let's think about how we're going to get these rates, because I can't simply have these rates that I'm talking about be the R in and the R out. These values of R were in gallons per minute, right? That's basically the solution. How quickly are we pouring solution in? I want to convert how the solution coming in relates to the amount of salt in that solution coming in. So it's not as simple as just saying, oh, well, that's not going to change because R in was equal to R out. That was the rate of change in terms of basically gallons per minute. We need pounds of salt per minute. So how do we get that? Well, if we look at our units of all the stuff that we have over here, and we want to figure out how to combine them to ultimately get what we're looking for, which is, again, try to get this all on one screen at once, pounds per minute, we're going to have to come up with a way of combining all of these things over here. And we can do it in a semi-intuitive way. So let's think about this, just for simplicity's sake, I'll call it capital R in minus capital R out instead of having to rewrite this whole phrase each time. So R in is the rate of Q that's coming in. R out is going to be the rate of Q, the rate of pounds of salt leaving. And let's think about them individually. So think about R in. How much salt is coming into the tank every minute? Well, we know that it's coming in at a rate R, but R is given in gallons per minute. So we have R gallons per minute of fluid coming in, and we ultimately need pounds per minute. So that means I need to multiply it by something that will give me the correct units of, so let's leave a blank spot here. This is basically going to be a blank spot. What units do I need to multiply by so that I get units of pounds per minute? Well, right now I already have minute in the denominator, so that matches. What do I have to put over here for these units to cancel with these units and give me these units? I already have minutes in the denominator, but I need to cancel out this gallons in the numerator. So I'm going to cancel out the gallons in the numerator by putting a gallons in the denominator. Therefore, when I multiply this term times this term, the gallons will cancel. To get the pounds in the numerator, I must need pounds in the numerator here. So if I multiply gallons per minute times pounds per gallon, I should wind up with cancellation of those two terms and get the correct units of pounds per minute that we're looking for. But which of our quantities had units of pounds per gallon? Come back over here. Well, that's the concentration of our input. So it makes sense that the concentration of our input should relate to how much salt is coming in. If I know how many pounds per gallon are coming in, and I know how many gallons per minute are coming in, then I can multiply those together to get how many pounds per minute are coming in. So our R in is just going to be multiplying R times C, whatever these values happen to be. What is coming out? So I want to make the same argument. I already know that it's flowing out at the same rate, right? The R out, lowercase r out, is the same as R. It's flowing out at R gallons per minute. I need some concentration here. Clearly, concentration was the appropriate thing that gave me the units I needed for everything to line up. But the problem is, if we come back to our picture, I don't know the concentration that's leaving. But how can we figure out that concentration? So this is going to be, we need to multiply it by the concentration that's leaving. So this quantity, that whatever I put here, it needs to be the concentration that's going out. Right? This quantity was the concentration going in. This needs to be the concentration going out to give us the appropriate units, which will be, I guess I shouldn't do equals. I should do an arrow here because it's not equal to 1 pound per minute, but just has units of pounds per minute, I should say. So how do we figure out that concentration? Well, I don't know the concentration, but I do know at any given time, Q is the amount of salt in here. Q is the thing that we're trying to keep track of. It's changing over time. So Q is a function of T. At time T, there are Q pounds of salt in here. What's the second thing I know? I also know how many gallons are in the tank because the tank is V gallons large. There are V gallons of fluid. So instead, if I simply say that I take Q, the unknown amount of salt in the tank, and divide that by V, the known volume of the tank, well, this is V gallons and Q pounds, and I get, again, the same units that I need to cancel. The idea is this Q is unknown. So The only term we don't know is Q. Right? The other things should all be prescribed somewhere in the problem. If you were given a problem like this, they would specify the value of R, they would specify C, they would specify the size of the tank, and the question is, Q is really the only thing that we're keeping track of trying to find. But that's okay. That's fine, because that's what we're trying to solve for. We are trying to solve for Q. So, if I put these quantities that we just came up with here in place of my R in and my R out and set them equal to dq dt, we get the following. dq dt, the rate of change of salt in that tank, is the rate in, which was R times C, both of which should be given in the problem, minus R out, capital R out, which is R times Q over V. So this is our differential equation. We have an equation where, again, R and C and V will all be known quantities. Q is the thing that we're trying to solve for, and it shows up in these two places in the equation. One is a derivative, one by itself right there. And if we want, we can simplify this a little bit and write it, clean it up a little bit. dq dt is equal to R times C minus Q over V, however you want to do it. Doesn't really matter. But this is our differential equation for mixing. It doesn't have a special name. This is our ODE for mixing. I'm not going to bother solving it. We'll talk about solutions of this again in the next chapter. But for now, this is how we can put a model together. And this is really one of the most important things I wanted you to take away from this problem is these things can be a pain in the butt to set up, but don't be afraid of doing some dimensional analysis. Dimensional analysis just means taking the units into account. I know what these units are. If it's equal to some quantity over here, these have to have the same units. I can't have apples equals oranges, right? We have to have the same units on both sides of any equality. And if you let the units kind of be your guide, it tells you how you should arrange these terms. It tells you what combinations you need to multiply together to get the desired units. So don't be afraid of units. I know this is something that's hard. A lot of times in math classes, units are kind of an afterthought. You do all the problem, you do the calculus, whatever it is you're doing, and at the end you say, oh yeah, I think this was supposed to have units. Maybe it's like newtons or something. I don't know. And you just toss it in at the end. Try to get out of that habit. It's a really hard habit to break. It's a habit I had for a really, really long time. But honestly, more often than not, if you keep track of the units all the way through the problem, they're going to make your life easier, not harder, once you get in the practice of doing it. They can inform you of what the next step should be. They can help you catch if you've made a mistake somewhere. And keep in mind that taking a derivative, dq dt, taking the derivative ddt of q changes the units. Q has units of pounds. This dt is a small amount of time, and it's in the denominator, so it's going to have units of time, minutes in this case, in the denominator. So just be aware of these things. They, in the long run, will help you. Keep in mind that, again, there's always limitations to these models. This model assumes that whatever is coming in is getting perfectly mixed before it leaves. Right? We made this assumption about the input rate and the output rate being the same. If we relax that condition and have the rates be different, we can still actually solve this problem. We'll see examples where we change it so the rate in and the rate out don't necessarily match, so that this value of R and this value of R are in fact different values. And it changes some things because, for example, the volume will no longer be a constant. We can't just use V for the volume of fluid in the tank anymore because the volume of fluid would be changing. But we'll talk about that when we actually get to solving these equations. For now, I just hope you've gotten a little bit comfortable looking at how we can kind of think about problems, try to break them down into common sense ideas, and find ways of combining those common sense ideas mathematically. So that's really the exercise here is, can you match your intuition, real world intuition, to your mathematical intuition? And can you find a way to use them in conjunction to come up with a model that's going to be useful? I would encourage you, if you'd like, to go read this section 1.3, read the textbook. There's a ton of other models that I didn't cover. It goes over things like radioactive decay and electrical circuits and this, that, and the other. Check them out. A lot of those models wind up looking very similar to the ones that we just did here, but it might give you a little bit more of an expansive view of some of the uses of differential equations and their physical applications. So, good luck.